Now we're going to take a box, and instead of pushing it, tying it to a rope, we are going to let it slide down a hill. What we're not going to do just yet is add friction. So I want to emphasize a few things. I keep saying it, but let's make sure that you have this down. The force normal is always perpendicular to the surface. And the force of gravity, always points towards the center of the world. So centered, just straight down. Gravity points to the center of the earth. Points to the center of the earth. And I have dogs. Center of the earth. All right, so let's see why I'm emphasizing that. It's because we're going to look at this, and the very first thing I want to do is a free body diagram. So what I think makes this a little bit easier is if I do it directly on the picture itself. And what I do to make sure that I'm pointing straight down towards the center of the earth is, you'll see the first thing I did is drew this line. It's exaggerated, to be sure. I made sure that it's perpendicular to this horizontal surface, because that to me is my guide that I've made sure that this is indeed going straight down towards the center of the earth. So this one would be my force of gravity. Then the other one, the force normal, perpendicular to the surface. Before, we've been on flat ground. So it's always gone straight up, which can be deceiving, and you can start thinking that you need to like keep going straight up, that it would go completely opposite from the force of gravity. But no, it's perpendicular too. So I'm going to very carefully draw a straight line up, and there is my force normal. Now on this one, there is no force of friction. It's just telling us that this is going to slide down the hill. In our next lectures, we'll introduce the force of friction, but for now there is none. So this is it. It has gravity acting on it, and it has the force normal. So what is accelerating it? Because remember, in the other videos, I've had that the force normal equals the force of gravity. So pause this for a second and see if you can't rotate this and maybe get a sense for what is happening. The first thing I'm going to do is kind of draw a line like this, or dot. This is an extension of my force normal. So I have this angle here between the normal and gravity. And what you'll hear is, you'll hear us refer to it as the angle to the normal. So gravity's angle to the normal, well, as it turns out, is exactly the same as the angle of the incline. And if you want, you can think of this as like a swinging. If I had a nut hanging on a line, you can't see my hands. If you had a nut hanging on a line, as I tilt the line, the amount that I'm tilting it here is exactly the same as the angle between the swinging bob, if you will, and the thing holding it. Well, the same thing happens here. And if you gotta get yourself, what are they're called a T. If you have a T line, you can take a piece of string and hang a nut from it, and just start rotating it. And what you'll see is that the amount that you rotate it is how much it swings. You can also prove this through similar triangles. And Sal from Khan Academy does a great job on that. So you can take a look at that video. But I'm going to redraw this. And what I'm going to do, which makes some of my counterparts unhappy, is I'm going to rotate it and put the force normal completely on the y-axis, just to make it visually more clear what I'm doing. So here's my force normal, all on the y. And I look at this, I'm like, okay, so the force of gravity is swinging this way, so it's coming out this way from the normal. There's my force of gravity. So the angle of this incline then, if I draw the axes down, here is my 22 degrees. So remember on the others, when I've done some forces and some of the videos with the vectors, I drew in there on something like this. I'm like, okay, so this is my y component, and this is my x component of the force of gravity. So tell me this, which one is accelerating it? What's going to cause that box to slide down that hill? Well, let's see, I have the y component of gravity is being counteracted by this force of normal. So that's what's keeping it from leaping off of the hill or plummeting through the bottom of the hill. It is indeed sliding, but it's sliding on the x-axis. So make sure that that feels comfortable with you. I have this net force that comes from that gravity component that is going to accelerate it this way along the x-axis. So I can write out my sum of forces now, that I have a sum of forces in the y. Let's see, I'll do to the right and up as positive, so I have the force normal minus this y component of the force of gravity. So this is one that gets people a lot, because you look at this and you say, well, that's the y, and so you're going to use sine because that's what you've used all the time. But look at this. This is the angle, and this side is adjacent to that angle. That's cosine. So this is the force of gravity times cosine of this 22 degrees. Now I ask myself the same question. With this rotated axis, am I shooting up into the air or falling through the earth? I'm moving in only the x. I have nothing in the y. So this equals 0. So if I'm asked, if I wanted, I can define then that the force normal here is going to equal the mass of that box times the acceleration due to gravity. And let's just define gravity again, 9.8 meters per second squared, times cosine of 22 degrees. That's my force normal. So cosine and sine, those things work between values of 0 and 1. At 1, my force normal, this would be what? 0 degrees, cosine of 0 is 1. So when this thing is flat, is that my normal equals the force of gravity. So cosine of that, and then cosine of what else does that? Play around with that. And so force normal then is decreased by this angle. So if it's decreased, well, that helps you think in terms of this thing called friction that we're going to delve into. But for today, let's look at how can I solve for this acceleration? Well, the thing doing it is the sum of forces in my x. What do I have? This is the opposite side, not the adjacent side. So this is my force of gravity times the sine of 22 degrees. That equals this mass times acceleration. So then I can look at this and I can rewrite my force of gravity, and I can go mass times gravity times sine 22 equals mass times acceleration. Now I kind of feel like I can cancel those two things out. Don't you? I have a mass on both sides. So doesn't that mean that these guys cancel? Mass divided by mass would give me just 1 because they're the same value. So didn't I just say then that if something is sliding down a hill, its acceleration is going to be g sine theta, which is an equation given in your book. What? Don't be in the habit of just grabbing those equations, because the very next thing we're going to do is friction. You need to be comfortable with how you get here, and you need to show how you get here. You can't just show me an equation. I need to know where your equations come from. Your equation sheets in your life should consist of just understanding your forces. So you can generate all of your own equations. I don't want anything just pulled out of thin air. Don't do that, right? So there you have it. We've solved for the acceleration of this thing, and we learned something here, that acceleration doesn't depend on the mass of a thing going down a hill. So that tells me that everything going down this hill is going to have the exact same acceleration. That's pretty cool. And actually what you'll see is the very next thing we'll do after we're done with forces is projectile motion. I'm not sure what that sound is. Hopefully the husband isn't breaking the kitchen. But you'll see when we do projectile motion, we never ask what the mass of something is. We derive some equations and we use them to define that motion. But gee, the acceleration due to gravity is the same no matter what. Well, that's all this is saying, is that everything under the influence of gravity is going to accelerate at the same rate. In fact, if you look on, I'll post it, if you look for the moon launch, one of the things that they did was tested that, and it was very exciting. He held a feather and a hammer, and he let them both go at the same time. And as he was doing it, he's like, let's find out if this is true, if they both accelerate. And lacking an environment, they both fell at the exact same rate and hit the ground at the exact same time. It is very cool. So that is something that we're going to enforce even more in projectile motion after we're done with friction. This is the last one for this, and now we move on to friction.